Hey everybody, another programming video today. So I recently got a suggestion, and it was a good suggestion, that I make a video on how to program a TSR, which I thought was a good idea because there's actually not a lot of good information on how to program TSRs for DOS on the internet, or at least on YouTube. So I thought, okay, let's make a video about that for anyone who's interested, which is probably only about 5 people, but still for those 5 people, it might be an interesting subject, right? So I guess probably a good first place to start is what is a TSR for those who don't know. TSR stands in this context for a terminate-and-stay-resident program. What that means is, most programs, when the program finishes, when you close the program or stop the program, uh, it just goes away and that's it. It stops running in memory. But a TSR is a program that terminates but stays resident in memory. It still stays running in the computer memory after it. It doesn't really terminate, but I mean it terminates in the sense that it returns you to the command prompt. Today in Windows, these would probably be called, or not only in Windows, I guess probably in other operating systems, it would probably be called something like just a background process, something that runs in the background. But in the days of DOS, DOS wasn't too heavy on multitasking. DOS could do multitasking. It was capable of doing multitasking, but people didn't usually use it in a multitasking way. And so programs that stayed running in memory were called TSRs, meaning they would return you here, where we are now, to the command prompt, and it would look like they were done running because you would be back at the user console, but the program would still stay resident in memory. So that's a TSR. So what's the advantage of a TSR? Well, obviously, similar to programs that run in the background today, a TSR can do things in the background while still letting you use your computer. It lets you, use the computer normally, but it may still be hanging around in the background, ready to do something when you need it, or doing something without you having to actively do it. So, the suggestion that I got was to make a TSR that controls the NumLock status, which I thought was also a good idea because that's something simple to do. The NumLock status, and actually all the 3 lock keys, so there's NumLock, Caps Lock, and Scroll Lock, and all of those are just 1 bit in memory. So why not just make a program that sets that 1 bit in memory and then just keeps doing so? So let me go ahead and explain to you the basic idea, the basic process of creating a TSR. There's a basic sort of framework for it. And it's not too terribly complicated, but I should I should say ahead of time, making TSRs is a bit of a black art. It's a little bit tricky sometimes. This is something which you probably shouldn't mess around with this too much if you don't know what you're doing. Well, I mean, these days there aren't many production computers running DOS anyway, so if you're doing this, you're most likely just doing this as a hobbyist or somebody experimenting, so I guess that's okay. But I wouldn't really do this on a production DOS machine unless you're really sure of what you're doing, and it might become clear why that is as we go on. So let me go ahead and go into my directory for A86, which just happens to be the assembler that I personally use because its developer is a cantankerous old guy like myself. And let's go ahead and use the editor, which I've actually copied from FreeDOS. This is actually the FreeDOS editor. And let's make a program called no numlock.asm for a program which prevents you from turning on the numlock. So again, let me go ahead and explain the basic process of making a TSR. I guess let's start at the beginning. So let's put a quick comment up here. A TSR which prevents numlock from being activated. Actually, that's technically, I guess, a misnomer. This doesn't actually prevent numlock from being activated, but it turns off numlock. If you ever turn on numlock, this program will turn it off right away. So how do you make a TSR? The first thing you want to do, let's go ahead and write these out. So step 1, get the interrupt vector of interrupt 8, software interrupt 8. What is interrupt 8? Let me actually quickly save this and kick out to help PC. And let me just show you the information here that this program has on interrupt 8. So interrupt 8 is the system timer interrupt. It is generated, as you can see at the bottom, it's generated 18.2 times per second by the PIT, the Programmable Interval Timer, which was a very important chip in the original IBM PC. It was called the 8253. That was the model number, and here's a bunch of information on it, which I'm honestly not going to I'm not going to read all of this. This is also the chip that you would use if you wanted to make sounds. Somewhere in here is information, I think, yeah, it's all kind of jumbled in here together. There's a lot of information here, but this is the chip that you'd use if you want to play sound effects on the internal PC speaker. Yeah, using counter 2. There you can see counter 2 is used for the cassette and speaker functions. That might be a topic for another day. I'm not going to get into that now, but so yeah, the programmable interval timer generates interrupt 8, 18.2 times a second. And the execution normally takes approximately 100 microseconds. This is kind of important for timing. Actually, it's very important for timing in DOS because, as many of you know, most of you who are classic DOS gamers know there are a lot of DOS games which were just programmed to run as fast as possible because they were released in the times of the original IBM PC or XT at a time when, you know, the computer ran at something like 8 megahertz, and that was the top speed of the computer. And then those programs run way too fast on more recent computers because they're clocked to the speed of the CPU. So a way to get around that, the way that well-programmed games, like Alley Cat, for example, Alley Cat is a great, it's a very well-programmed DOS game because it runs at an appropriate speed, even if you run it on like a 486 or Pentium class computer. How does it run so well? Because it doesn't just use the CPU count, the CPU clock cycles count. It uses a timer that's tied to real time, which was usually this. It was usually based on that 18.2 times per second, you know, that 18.2 hertz interval generated by the programmable interval timer. So interrupt 8 is very important to the operation of the PC, and you probably shouldn't mess with it. But that's exactly what we're going to do. We're going to mess with it we're basically going to change how interrupt 8 works in order to create a TSR. So let me go back to my program, and I will start editing the program again. No numlock.asm. So what do we do? The first thing to do is use a CLI opcode to turn off hardware interrupts, because the last thing you need is a hardware device like a sound card or any other hardware device suddenly generating a hardware interrupt in the middle of you messing with the PC's interrupt routine. So we turn off, we always use CLI when we do work like this, and we can turn on hardware interrupts later when we're done here. So what do we want to do now? We want to get the interrupt vector of interrupt 8. Some time ago, some months ago, I made a video showing how you can actually directly see the memory locations of interrupts. I think they start at address 0, like they're literally the first thing in the computer's memory. And I made a video about looking at that directly with debug back in the day. But if you want to do that in a more excuse me, if you want to do that in a more socially acceptable way, in a way that's considered safer, then you use the interrupts provided by DOS. DOS provides interrupts to get interrupt vectors and set interrupt vectors for various interrupts. So what we do is, right, interrupt 2135 gets an interrupt vector, which means basically just the address, the memory location, or the address of that interrupt in memory. Again, interrupt 21 should be familiar to DOS programmers. It's the sort of Swiss Army knife interrupt provided by DOS. So what do we want to do? We want to move 35 into AH to indicate that we're running sub interrupt 35. And we want to also specify which interrupt we want. We want interrupt 8. So we want the vector, which means the memory location of interrupt 8. There we go. And now we just run interrupt 21 hexadecimal. Boom, that's it. Step 1 is done. So what this does is it sets ESBX. So ESBX is now a pointer to the interrupt routine for interrupt 8. ES is a segment pointer and BX is the offset pointer. Okay, what do we do now? If we were doing this properly, what we should do now is, let me go back to help PC for a second. Whoops, didn't mean to do new, meant to exit. So if we go back to help PC and run this again, what did it say about interrupt 8? It says here, interrupt 1C is invoked as a user interrupt. So I think what you're supposed to do, yeah, and this is directly called by interrupt 8, so approximately 18.206 times per second. This is what you're supposed to use for a TSR. If I were doing this properly, I think this is what you should use to make a TSR. But many, many years ago, about 20 years ago, I actually wrote a program that functions as a TSR, and for some reason I remember somebody telling me to use interrupt C8. I don't know if there was any reason for that. As far as I know, you can use any interrupt number that's not already being used. There are lots of free interrupts that are not used by anything in the computer, and so you could use any number that you want, potentially. But somebody told me that I should use interrupt C8, and I really don't remember now why that was, if that was just some number that they just picked out of the top of their head to tell me to use, or if that was something. Actually, I'm not even sure if I might have just made that up out of the top of my head. Who knows? This was 20 years ago, and I don't remember my reasoning for using interrupt C8 anymore, especially since it says here quite clearly that the user routine should probably be interrupt 1C. But what I will go ahead and do, since this is how I did it, I'll just go ahead and do it how I did it 20 years ago. Live a little dangerously. It's not really that dangerous if you know what you're doing, which I don't. But step 2 is to make another interrupt behave like interrupt 8. We do this by pointing another interrupt, a different interrupt, at the vector for interrupt 8. So you can set, let's see, you can set an interrupts vector using int21. What's the sub interrupt is 25, I believe. Yeah, I think it's 25. So what you need to do is set DSNDX to be to the desired vector point, set AL to the interrupt number, and I think that's it. Yeah. And then just call interrupt 21H. Yeah, that's it. That's all we have to do. So we have ESBX. So the interrupt for the vector for interrupt 8 is an ESBX. We need to transfer that into DSNDX. So the second half, like the actual offset is easy. We just say move BX into DX. That's it. That's all you have to do. But getting ES into DS is a little harder. You can't just say move DS ES. The Intel CPU the Intel 8086 CPU architecture doesn't have a command for this. So what you have to do instead of using this command, you have to do it indirectly by saying push ES onto the stack and then pop DS, pop from the stack into DS. There you go. Now DSDX equals whatever ESBX was, and actually probably still is, but it doesn't really matter now. Okay, good. And then we just have to set AL to C8 hexadecimal, because that's the interrupt that we're going to use for reasons that just because I'm too stubborn to use the proper interrupt, I guess. And then, yeah, and then we, in AH, we stick 25 hex in AH to tell interrupt 21 that we want to set the interrupt vector, and that's it. Interrupt C8 now points to the code location of interrupt 8. So in essence, C8 does exactly what 8 does. Interrupt C8 does exactly what interrupt 8 does. They both point at exactly the same place. So if you call either of these interrupts, they should do exactly the same thing. Why is that important? Because we are going to hijack interrupt 8. We are going to hijack it to do what we want. So that's step 3. Set interrupt 8's vector to your own TSR routine. So once again, we use interrupt 2125 to set the location, or to set the vector of that interrupt. So what we need here, we need a code point. We need a place in the code where we're actually doing the thing that we want to do. So let's go ahead and I'll just put down here a point called our TSR code. This is the point where where the TSR actually does the thing that we want it to do. Good. That's easy enough. Then we just need to say, so hold on, we need to set, again, we need to set DSNDX to point to our TSR code. So how do we do that? Easiest thing to do is to say push CS. This will push the code segment, which is the segment where our code is, where this code is currently running, and then pop DS. Sets DS to equal the code segment where this program is running. Where this program is running now. Good, that's it. So now DS points to, this segment, because it's, where the program's running. And then we just say move DX offset our TSR code. And the assembler, I don't know exactly what offset this will have, but the assembler is smart enough that when you assemble this program, it will put the actual address of our TSR code here into DX. So, fine. Done. And now, once again, we say move AL. Now we've set AL to H because we want to change the vector point for interrupt 8. And again, yeah, move 25 hexadecimal into AH to set interrupt vector point. And then just call interrupt 21H. There you go. Done. What has happened? At this point, we have just set interrupt 8, which is that interrupt which the computer calls about 18 times every second. That interrupt routine, instead of doing what it usually does, instead of doing what it's supposed to do, now it points at our code here. And whatever we put after this point, the computer is going to run 18 times every second. It's expecting to do a timer routine, but it's going to get the surprise of its life because instead of running a timer routine, it's going to run what we tell it to run. So, yeah, and then step 4 is, do interrupt 2131, and you're done. So, let's let's see. So you're supposed to put the exit code for batch files into AL. Let's just do 0. 0 is fine. I mean, we don't really, for this purpose, we don't really care too much about the batch file exit code. DX is supposed to contain how much memory we reserve for this TSR. Let's go ahead and reserve 255 bytes of memory. That should be more than enough, I think. I don't think this program is going to be 255 bytes long, so how much memory is reserved for this TSR? And then, yeah, and then we call interrupt 2131. So we move into AH 31 hexadecimal, make this into a TSR, and then we do interrupt 21H. Boom, done. Our program, when we run it at this point, it is now loaded in memory. It is resident in memory. It will stay in memory. You can't really get rid. There's no way to get rid of the program now unless you reboot the computer. And this interrupt 21 will return control to the user. It will return you to the command prompt, but the program will continue running in memory as a TSR. So that's it. That's the basic principle of how to make a TSR. What you're going to find, however, is that this will probably crash the computer instantly because the usual interrupt 8, which is supposed to run, is not running anymore. So how do we get around that problem? Yes, we've hijacked interrupt 8. You can do that easily enough using the code that we see here. But how do you prevent this from crashing the computer? Well, I will show you. First, before we do anything else, let me run a CLI again. I don't know if this is actually necessary because theoretically the interrupt flag should still be off, meaning interrupts are still disabled, but just to be on the safe side, let's disable interrupts as part of the interrupt routine. And I'm gonna go ahead and put here as a placeholder for now. Here we do the thing we actually want to do. But I'll fill that in later with what we actually want to do. What we want to do is here call interrupt C8. Because remember, C8 points at whatever the old interrupt 8 used to be. So you want to make sure to do this. Make sure to do this as part of your TSR code. Call the old interrupt 8 using the placeholder interrupt. In this case, I used C8, but you can use whatever interrupt you want to use that's not already being used by something else. Make sure that you don't forget to call the old interrupt 8, because otherwise you're going to crash the computer, probably. Or at the very least, something really weird is going to happen with the computer. So we call the old interrupt H to make sure that we, that everything we do is kosher. And then at the end, we do this. We move 20 hexadecimal into a register. Here I'm using AL. Doesn't really matter. I mean, it can be any register. And then you output to hardware to IO address 20. So you output 20 to 20. Output 20 hexadecimal to port 20 hexadecimal. What this does is this sends an end of interrupt signal to the 8259 interrupt controller. That's important because it needs to know when the interrupt is done. You need to tell it the interrupt is done. Then at the end you say STI to re-enable hardware interrupts, and then do an IRET, which means return from interrupt. Signifies that the interrupt is over. That's it. That's the program, ladies and gentlemen. This program is now a functioning TSR, and it should not crash the computer because all we're really doing is we have our own routine here to call the old interrupt 8. So instead of calling the usual interrupt 8 jumps into our TSR code here, and then our code does, here we do whatever we actually want it to do, and then at the end, don't forget, run the old interrupt 8. And that's it. As long as you do all this, the computer shouldn't have any problems. It's because it's basically doing exactly what it did before, just from a different memory address, right? It's invoking a different, slightly different routine, but it doesn't really matter too much. This will do whatever interrupt 8 should have done, and this should keep the computer running just fine. So that's basically it. Now we're free. We are free here to put whatever we want to do. Here we can put whatever code we want, and that's the code that will execute 18 times a second. Nice. So I want to, before I get started, I want to just put a little bit of framework around this because we need to do a little register preservation. First of all, before we do anything else, let's do a push A and a push DS because I'm going to be using both of these. Push A, what does push A save? I believe, hold on, let me save this quickly and check in help PC again. Push A, wait, wrong section. There we go, push A. So push A pushes AX, CX, DX, BX, SP, BP, SI, and DI. It does not push DS. So if you want to conserve DS or preserve DS, you need to do that separately, which is why I did that separately. So, right. So push A preserves, what was it? I believe at least AX, BX, and CX, etc. I think we're just going to use AX and BX here, and then also DS. So we need to separately push DS. And then when we're done, after we've done the whole thing that we do, before we call interrupt, before we run the old interrupt 8, because we might have done something weird with the registers here. So in order to not screw up interrupt 8 by doing something totally strange with the registers, we need to pop those registers in reverse order. So pop DS to restore DS, and then pop A and everything else, or at least AX, BX, etc. Yeah. So that's something that you want. If you're going to use any registers in your code, make sure to preserve them first with a push and then restore them afterwards with a pop. That is very important. And that also goes for this part here because this, we're changing AL here. So before we do this, let's go ahead and push AX because we're using AL here and AL is part of AX. So we push AX at the beginning here, and then afterwards pop AX to restore it to whatever it was before. I think that is it. Did I miss anything? I think that's it. Okay, so that's it. We have done now all the necessary precautions and safety measures that we need to take. So let me just go ahead and save this quickly and go through the code again. So this is your basic kind of skeleton for a TSR. Get the interrupt vector of interrupt 8, or probably interrupt, what was it, 18, or whatever it was, whatever one you're supposed to use if you're doing this properly, which I'm not. And then point another interrupt to interrupt 8, and then point the current interrupt 8 to your own TSR routine, to your own code, and then just call, do this to indicate, to tell the computer that you're done. And don't forget to save your registers, and then at the end you do this to tell the interrupt controller that the interrupt is finished, and then you do this to return from the interrupt. That's it. That's the basic skeleton of an interrupt, and now, like I said, we can put here anything that we actually want to do 18 times a second. So what we want to do with this program was turn off the NumLock. So the NumLock is in, where is it in memory? Let me once again go back to help PC. And I think there's a topic here called, yes, memory map. So let's actually check the memory map here. Where is it? It's at, oh wait, I think I went too far. Yeah, it's already here. So it's at location 4017. So you can see it in memory byte 4017. This is a byte, and all the 8 bits here have significance. So the second bit, bit number 6, controls caps lock. The third bit, bit number 5, controls NumLock. And the fourth bit controls scroll lock. So what we need to do is, if we want to force NumLock to be off, we need to force the third bit of location 4017 to be 0. That's all we have to do. Easy, right? It is actually fairly easy. So we come down here. Right, here's where, yeah, okay. So change the third bit of memory location 4017 to be 0. That's it. That's all we have to do. So let's go ahead and set the data segment to point at segment 40 hexadecimal, because these numbers here are, of course, hexadecimal, not decimal. So set the data segment to point at 40. And we'll use BX as an index register, so we'll set BX to point at 17. Now we move into AX. Crud. I cannot. Gosh darn it, I cannot type square brackets here properly because the editor, I need to hold down the Alt key to do that with my German keyboard, and when I hold down the Alt key, it thinks I want to access something from the menu, which I do not want to do. Let me see. Can I say keyboard US? Will that make it work with the, let me try it now. Let me see, can I now type, there we go. Yes, thank you, it works. Okay, good. So, if you do this, this will move the contents of BX into AX, but if you put square brackets around BX like that, it uses BX as a pointer, and it moves the memory location, it moves the contents of the memory location that BX is pointing at into AX. So now we have the current contents of 4017 in AX. What do we do with it? We AND it with 110, 11111. And I'll put here XB to indicate that that's a binary number, because we need to change the third bit to be a 0. And if we AND all of these bits with 1, they'll remain unchanged. But if you AND this one bit with a 0, that forces it to be 0. So AX now contains whatever that memory location had, except that the third bit is a 0. And now we just go back. We just move it back into BX. So move back into the memory location pointed to by BX, the current contents of AX. And we are done. That is literally it. Making a TSR that forces NumLock to be off is that simple. Let's go ahead and save. Let's go ahead and run it. No NumLock. I got no errors. That's a good sign. So let me do a test now. I'm going to go ahead and, let's see, if I type a bunch of stuff, I have NumLock off right now. So if I press 4 on the numeric keypad, it works, yeah, it works like a left arrow. It goes to the left. If I press 6 on the number keypad, it goes to the right. If I turn NumLock on, NumLock is now on. Now if I press 4, it works not as a left arrow, but as a number 4. And if I press the number 6, it works as a number 6 and not as a right arrow. So now, let's go ahead and run no NumLock. And let's try this again. So now I'm going to type a bunch of stuff, and let's see. So NumLock should be off right now. So yeah, 4 works like a left arrow, 6 works like a right arrow. I turn NumLock on, and oh, that's interesting. It did it the first time. I've never seen that before. That's interesting, because I've tested this program before and I've never seen it do that. That's bizarre. Why did the very first time the NumLock worked and then it turned it off? I wonder if that's something funny that DOSBox is doing. Maybe DOSBox doesn't check, or maybe it doesn't run TSRs until something happens, until you press some kind of key. That's interesting. I'm more inclined to suspect that that's a quirk with DOSBox than a problem with the program itself, because I tested this program on a real DOS PC 20 years ago and I never saw something like that. So that I suspect that might be something funny that DOSBox is doing with the TSR, but I'm not too worried about it. But yeah, and now if I press my NumLock key, it's actually kind of funny. If I press NumLock on the keyboard, the light on my keyboard, the little LED on the keyboard to indicate the status, actually does change. But you can see in DOSBox, I'm not typing 4s or 6s. It's still working. So basically in DOSBox internally, NumLock is off, but it is not setting the status of the key on the keyboard. I'm pretty sure, I'm very sure the reason for that is because this is DOSBox. If I were running this directly on a real DOS PC, it would definitely turn the keyboard light off. It's just that my computer is not actually checking. It's not checking what DOSBox thinks. It checks what Windows thinks, because I'm running this in I'm running DOSBox in Windows. So the keyboard gets its information from Windows. If this were a real DOS PC, the keyboard light would also behave correctly. So the keyboard light is not properly reflecting what it's doing, but you can see in either case when I press NumLock, whether the light on the keyboard is on or off, it does not work in DOSBox as a NumLock on. So it's basically forcing NumLock off. What you could do if you're very fast, let me try to do it really fast. Oh, it worked. If you're very fast, yeah. Yeah, if you're very fast, because basically it turns off NumLock 18 times a second. So if you very quickly press NumLock and then a key on the numeric keypad, it will work. It will type it as a number, because you have basically, you have like a 1/18th of a second to press the key before NumLock turns off. So yeah, it's not perfect, but that's the idea. That is a TSR. That is how a TSR works. Now, just as another example, let me show you what I did several years ago when I wrote a TSR. I made a TSR to force a pixel on. So what I'm going to go ahead and do is I'll say copy no numlock.asm, copy it to, I called it permpixel.asm, permanent pixel, because it permanently leaves a pixel on. So let me go ahead and get back into, oh, crud, I need to figure out the keys now because I'm using an English keyboard layout on a German keyboard. There we go. So a TSR which forces one pixel to remain on. So this program works similarly. We just need to change we don't need to change much except the actual, except this actual code here that does the thing we want to do. So to do that, let me check the code. What did I do? This is all so long ago, I don't have the details in memory, but it's pretty simple. I mean, it's basically just setting one, pixel on the screen. So what you need to do, hold on. I think what I did, trying to think what, okay, let's go ahead and do this. Before we do anything else, let's go ahead and set a graphical video mode, because obviously you can't change graphics pixels on the display if you're not in a graphics video mode. So I'll go ahead and say, let's see, interrupt 10 controls is the graphics interrupt. So we need to move, let's see, right, so we move 0 into AH. This tells it to set the video mode. And then let's use the venerable mode 13 hexadecimal, which is 320 by 200, 256 color VGA. Okay, good. So now this will, so hold on. So the above 3 lines just set the video mode. That's something we'll probably want to do before we do anything else. And right, so all this code here, we can get rid of this. This is to turn off NumLock. We won't need that now. We need something entirely different. What we want to do here is write a pixel to memory. So what I did, how did I do that? Let me just quickly check, looking at my old program code. Where is it? Oh, here it is. Okay, I found it. Right, okay. Yeah, so the code as it is remains largely unchanged. We just, yeah, exactly. This part here just changes because we don't turn off NumLock, we turn on a pixel. So what I'm going to go ahead and do is set DS to be A000 hexadecimal, which is the start of the VGA video memory. And then we'll use BX as a pointer to that memory. I used location 35,100. This is the location of the pixel on the screen. Adjust to taste. You can change this to whatever you want as long as it's within the bounds of the screen. And then we set AX to be 44 hexadecimal, which happens to be a nice yellow color, which I liked using for these tests because it's kind of bright and visible. And then, I mean, you can also change this to whatever you want. This is the color, so put any color value that you want in here. And then finally, we move, once again, using BX as a pointer, we move AX into the memory location pointed to by BX. And that's it. Once again, done. This is our permanent pixel program. This will keep moving 18 times a second. This will move the value of 44 hexadecimal into this memory location in this segment. And that will force that pixel to be on. So let's go ahead and see what it does. Go ahead and save it. Quit, say 86 perm pixel. Okay, I got no errors. That's a good sign. Let's run perm pixel. Yep, and there you go. You see in the kind of in the middle of the right-hand side of the screen, there's that yellow pixel there. And you cannot make it go away. You can type CLS. Why do I? Huh? That's interesting. It appears to have crashed the. It appears to have crashed DOSBox. The pixel's working anyway. The pixel's there, but I cannot type anything. The computer does not react at all to any input that I type in. Okay, that's interesting. I wonder why it did that. Let me kill DOSBox for a second, and I will restart DOSBox. And let me try that again. I wonder if it, let's see, perm pixel. Now it works. That's interesting. Oh, typing CLS. Oh, typing CLS in DOSBox actually resets the video mode. Okay, that does not happen in real DOS. In DOS, typing CLS does not reset the video mode, but DOSBox does that. But okay, but anyway, okay, but you can generate a bunch of Oh, that's interesting. If you run it a second time, okay, interesting. If you run two programs that do this at the same time, it makes DOSBox crash. That's probably because there are two things that are trying to do something at once. Because you've got two programs that are trying to snag the same interrupt routine. That's interesting. I actually never realized that. I don't think I ever tried this. I don't think I ever tried running two TSRs at the same time. I never realized that it crashed DOS. Yeah, it's like I said, I think it's pretty apparent that this is kind of a dodgy thing to do because you are literally, I mean, like I said, you're literally changing what a built-in interrupt of the computer does. Like you're literally taking the timer interrupt and making it do your own program code instead of what it's supposed to do, which theoretically should work, but it's kind of fraught with peril. There are a lot of ways that this can go wrong. There are, especially if you have a lot of TSRs. I mean, you can imagine basically what happens is if you have a lot of TSRs running and they all try to snag the same interrupt, you end up with this long chained routine in memory where several TSRs are doing their thing one after another 18 times a second because you've got all this TSR code running in memory and it just keeps running and they're all sort of chained off of one interrupt call. There's a lot there that can go wrong. There are a lot of ways for that to either create really unpredictable behavior or create very strange timing problems, or in this case, just to hang the computer, as it appears to be what happened here. DOSBox just completely crashed. Well, I think this illustrates pretty well why you shouldn't do this unless you know what you're doing. So that is how you create a TSR. That is the basic idea of how to make a TSR. You make a program that runs in memory, you give it its own interrupt number, and then it just keeps running. Have it call from interrupt 8, and it will just keep on running. Let me just go ahead and close DOSBox one more time and just kind of show you how that's supposed to work. I mean, how this permanent pixel program is supposed to work if it didn't keep crashing. So permanent pixel, right, here we go. So now I'm just going to type a bunch of gibberish, and you can see it keeps scrolling because, content on the screen does obviously scroll up, but the TSR, since it's still running and it runs 18 times a second, it does keep trying to replace that pixel. It keeps putting that pixel in memory. And you can kind of see it's I don't know how visible it is because it happens pretty fast, but I mean, if you press enter, actually you can see it missed it a few times. If you hold down enter for a bit, you can see some spots where it missed putting the pixel, where it actually scrolled twice before the TSR triggered and put the pixel back on the screen. So, because again, it only happens 18 times a second, so it's not like it's happening millions of times a second. It's fast, but it's not that fast. You can outpace it if you do something that happens faster than 18 times a second. So it's not perfect. And again, there are myriad ways to really screw up your DOS environment if you don't know exactly what you're doing. So that's why I said at the beginning, this is really a black art. I would not encourage doing this in a production DOS environment. But again, I know that most people probably aren't running production DOS environments these days. So if you want to experiment with this, it's a good bit of fun to play around with and try doing different things and see how it works. But do not, again, unless you really know exactly what effects this is having, do not trust yourself with this, because you can really screw things up in ways that are very difficult to diagnose because, again, because there's like timing involved, and timing problems like this are very difficult to diagnose sometimes. And especially if you have a bunch of TSRs that are all chained up in memory, and each one is like subsequently calling, like they're, TSRs and sub-TSRs where each one's linked from the same interrupt call. That's a disaster waiting to happen. So please do not do that unless you're just running a test system and you don't really care if it crashes, in which case, yeah, go ahead and have fun, which is what I did here. So yeah, that's how it works. That's how it's supposed to work. And I don't claim to be an expert on this. I might have done something wrong. I might have done something very bad and naughty that I wasn't supposed to do. If I did, please let me know. This is just what I learned 20 years ago. I learned how to do this 20 years ago, and this is more like a toy program. This is like a toy that some kid would make just to have some fun, which is exactly what I did with it. You know, I was a kid and made this program to have some fun. But this isn't really something useful, obviously. If you were making a TSR that does something useful, there's probably some other, some other safety checks that you should put into it to make sure that it's not going to smash the computer's memory or do something ridiculous. But this is just a basic idea. This is the basic principle, and it's fun. I hope it was fun to watch. I hope that it was at least mildly interesting for some of you. And yeah, that's it. I am gonna check out for now. So thanks for watching, everyone. As usual, I'm open to feedback. If anybody has any comments or ideas or suggestions, please leave them in the video comments. Ta-ta, everyone. I will talk to you all later. Bye-bye for now.